Welcome back. I'm Dr. Hodges, and welcome to another episode of Information Technology and Cybersecurity Explained. In this episode, we will explore network essentials. When I talk about modern computing, I always remind students that everything we do in IT begins with one fundamental idea: devices communicating with each other. Whether it's your phone syncing to the cloud, a server talking to a database, or a smart device in your home, all of these systems rely on the ability to share data across a network. But devices can't just exchange information randomly. They need structure, they need a common language, and that's where protocols come in. Protocols are simply agreed upon rules that define how data is formatted, transmitted, received, and validated. I often describe protocols as the grammar and vocabulary of the digital world. They ensure that two systems that have never met can still communicate perfectly. Examples you use every day include HTTP, HTTPS, TCP, IP, DNS, and Wi-Fi standards. You don't see them working, but without them, nothing in our digital ecosystem would function. This is why I say this concept is truly the foundation of all IT systems. If you strip away the devices, the servers, the applications, and even the cloud, what remains at the core is communication. Every part of IT relies on connectivity and protocols to move data securely, reliably, and at scale. As IT leaders, understanding this foundation helps us design better systems, solve complex issues faster, and make smarter decisions about architecture, security, and innovation. It all starts here with devices sharing data through protocols. When I think about the role of modern IT systems, I always emphasize that everything we do relies on one critical capability: communication. The moment two systems, two networks, or two organizations need to exchange information, we are relying on the underlying infrastructure, protocols, and technologies that make communication possible. Without this, there is no collaboration, no data sharing, and no connected business operations. But communication alone isn't enough. It has to be secure. That's why this same infrastructure also supports cybersecurity. Every firewall rule, every authentication mechanism, every encrypted session, these all ride on top of the communication layers that connect our systems. As cyber professionals, we know that security isn't something bolted on later. It has to be embedded into the way systems communicate from the start. The strength of our cybersecurity posture is directly tied to the strength, reliability, and architecture of our communication pathways. And this brings me to the third point: digital transformation. Organizations can't innovate, automate, or scale without strong communication systems. Digital transformation, whether through cloud migration, AI adoption, automation, or DevOps, depends on seamless, secure data flow across platforms. When communication is efficient and secure, organizations can adopt new technologies faster, integrate systems more easily, and operate at a level of agility that was impossible just a few years ago. So these three ideas, communication, cybersecurity, and digital transformation, aren't separate pillars. They are deeply interconnected. Strengthen one, and you elevate the others. As IT leaders, our job is to architect environments where communication is seamless, security is inherent, and transformation becomes a natural outcome. When I introduce the core building blocks of a network, I always start with the essential devices that make everything work behind the scenes. First, we have the router. I explain to students that the router is essentially the traffic director of the network. It decides where data needs to go, whether that's out to the internet, across sites, or between internal networks. Without routers, nothing would know the next hop, and communication would break down immediately. Next is the switch. If the router is the traffic director, the switch is the local connector. It links devices within the same network: servers, printers, endpoints, allowing them to communicate efficiently. Switches operate at lightning speed and form the backbone of internal network communication. Then we have the firewall, which I often describe as the network security guard. Its job is to decide what traffic gets in, what gets out, and what gets blocked entirely. This is one of the most important layers of cybersecurity. As we know in practice, a misconfigured firewall can cause outages, expose networks, or accidentally block critical traffic. So understanding firewall rules and architecture is essential in our field. Access points extend the network wirelessly. They're the enablers of mobility, allowing laptops, phones, IoT devices, and sensors to connect from anywhere in the building or campus. Access points form the foundation of modern flexible workplaces. And finally, we have the endpoints, the devices people actually use. Laptops, desktops, tablets, mobile phones, IoT devices, sensors. These are not only the consumers of network resources, but also one of the biggest sources of risk. Endpoint protection, patching, monitoring, and configuration management are critical to maintaining a secure ecosystem. So when you put these together, routers, switches, firewalls, access points, and endpoints, you get the core architecture of a functional, secure, modern IT environment. Every single digital experience we rely on every day runs through this stack. When I explain networking to students, I like to break it down into three simple layers: LAN, WAN, and the Internet. These three concepts describe how networks grow, from something small and local to something large and global. Let's start with the LAN, or local area network. This is the network inside a home, an office, a school, or a building. It's the most familiar to us, the place where our devices connect to switches, access points, printers, servers, and each other. LANs are fast, controlled, and usually owned by one organization. When we think about internal communication, file sharing, or internal systems, that's your LAN. Next, we scale up to the WAN, or wide area network. While a LAN is one location, a WAN connects multiple LANs together. So imagine a company with offices in Charlotte, Atlanta, and Dallas. Each office has its own LAN, but they still need to collaborate and share resources securely. The WAN is what ties those locations together through leased lines, SD-WAN, VPN tunnels, or cloud connectivity. It's essentially the organization's private highway between its different sites. Finally, we have the Internet, which is the largest network of all, a global network of networks. No single organization owns the Internet. It's a massive interconnection of millions of LANs and WANs across the world. What makes the Internet work is agreement on protocols, standards, routing, and cooperation between providers. Whenever we browse, stream, or access cloud services, we're riding across this global network. So, in summary, LAN is local and private. WAN connects those local networks across distance. The Internet connects everything globally. Understanding this hierarchy helps students see how networks scale, how traffic flows, and how organizations securely extend their reach across the world. When we talk about networking, one of the first concepts students must understand is the IP address. I explain it as the digital version of a home address. Every device, your laptop, your phone, your printer, your server, needs an IP address so the network knows where to send data. Without an IP address, a device is essentially invisible. Right now, the most common version in everyday use is IPv4. These are the familiar addresses like 192.168.1.10. IPv4 has been around since the early days of the Internet, and even though we're slowly moving to IPv6, IPv4 is still everywhere. Its simplicity and long-standing support make it foundational. Then we have subnets, and this is where we start moving from basic addressing to actual network design. A subnet is simply a smaller segment of a larger network. The benefit of subnetting is structure and control. It lets us organize devices by function, security level, or location. For example, you may have one subnet for servers, one for user devices, one for printers, and one for IoT sensors. Subnetting also helps reduce congestion, limit broadcast traffic, and improve security by isolating different parts of the network. As organizations grow, subnetting becomes essential for scalability and proper network hygiene. So when you put this together, IP addresses identify devices, IPv4 is still the dominant format, and subnets allow us to break networks into manageable, secure segments. Understanding these concepts is absolutely foundational for anyone entering IT or cybersecurity. When we think about how information moves across a network, even something as simple as loading a web page, it's easy to picture data traveling as one big chunk. But that's not how networks work. In reality, all data is broken down into small, manageable pieces called packets. I like to explain packets as digital envelopes. Each one carries a piece of the data along with instructions, where it came from, where it's going, and how it fits together with all the other packets. Once the data is broken into packets, they travel across the network independently. And this is one of the most fascinating parts of networking. Packets don't always take the same path. They choose the most efficient route available at that moment. If a network segment is congested or unavailable, packets can reroute automatically. It's incredibly resilient by design. Then, when the packets finally arrive at the destination device, they are reassembled back into the original data, whether that's a file, a video stream, a web page, or any other content. And all of this happens in milliseconds, completely invisible to the user. Understanding packetization is crucial because it explains how modern networks scale, how routing decisions are made, and why the Internet is so resilient, even when parts of it fail. This packet-based approach is one of the foundational ideas that makes global networking possible. When we talk about networking, it's not just about wires, routers, and IP addresses. The real magic happens through protocols, the rules that define how data moves and what that data means. Let me break down a few of the most important ones that you will use throughout your IT and cybersecurity career. First, we have HTTP and HTTPS. These are the protocols that power the web. Anytime you browse a website, load an app interface, or interact with a cloud service, you're using HTTP. HTTPS is simply the secure encrypted version, and today it's the standard. HTTPS protects confidentiality and integrity through TLS encryption, making it essential for cybersecurity. Next is DNS, the domain name system. I tell students to think of DNS as the Internet's phone book. When you type google.com, DNS converts that name into the actual IP address that machines understand. Without DNS, the Internet becomes effectively unusable. It's also a major target for attackers, DNS hijacking, poisoning, tunneling, so understanding it is critical. Then we have SMTP, the protocol that handles email. Whenever you send or receive email, SMTP is involved in routing those messages across mail servers. It's been around forever and is still core to business communication. Unfortunately, attackers also exploit email heavily, so securing SMTP through authentication, SPF, DKIM, DMARC is essential. SSH is next, and this is a big one for system administrators and cybersecurity professionals. SSH gives you secure remote command line access to servers and devices. It's encrypted end-to-end, and it's the preferred tool for managing Linux systems, network equipment, and cloud hosts. If you're doing anything in IT, you'll use SSH constantly. Finally, RDP, the Remote Desktop Protocol. RDP allows remote access to a full Windows desktop. It's convenient, powerful, and widely used in enterprise environments. But it's also one of the most attacked services in the world, especially when exposed to the Internet. Strong authentication, network segmentation, and monitoring are key when using RDP. So, these 5 protocols, HTTP, HTTPS, DNS, SMTP, SSH, and RDP, form the backbone of modern IT operations. They're essential, they're powerful, and they're also high-value targets for attackers. Understanding them is foundational to everything we do in IT and cybersecurity. When I walk students through modern infrastructure models, I like to show the evolution of how organizations think about systems, security, and connectivity. These 5 terms, on-prem, cloud, hybrid, zero trust, and SASE SD-WAN, represent the major pillars of today's IT architecture. Let's start with on-premises. This is the traditional model where servers, storage, applications, and security tools all live inside the organization's own facility. You own the hardware, you manage the network, and you control the physical environment. On-prem still matters today, especially for regulated industries, legacy systems, and ultra-sensitive workloads. Next is the cloud. Over the last decade, organizations have shifted massively to cloud platforms like AWS, Azure, and Google Cloud. The appeal is scalability, flexibility, rapid deployment, and reduced on-prem footprint. Instead of managing hardware, we consume services. This model lets organizations innovate much faster, but it also changes how we secure and architect systems. The reality for most companies today is hybrid. It's a blend of on-prem and cloud. Some systems remain local, others live in the cloud, and integrations tie them together. Hybrid is often a strategic stepping stone during cloud migrations, and some organizations remain hybrid permanently because it fits their business and compliance needs. Now, as environments became more distributed, the old castle and moat security model fell apart. That's where zero trust comes in. Zero trust assumes no user, device, or network segment is automatically trusted. Every request must be authenticated, authorized, and continuously validated. Identity becomes the new perimeter, and security controls follow the user, not the building. Finally, we have SASE and SD-WAN, 2 of the most important modern networking concepts. SD-WAN is about optimizing and intelligently routing traffic across multiple WAN paths. SASE, Secure Access Service Edge, takes that networking layer and merges it with cloud-delivered security, firewalls, ZTNA, CASB, DLP, all from the edge. Together, SASE SD-WAN aligns perfectly with hybrid work, cloud adoption, and zero trust architecture. It gives organizations consistent security and performance no matter where users are located. So when you look at these 5 concepts side by side, they tell the story of modern IT from physical systems to the cloud to hybrid models, and now into identity-driven, cloud-delivered security architectures like Zero Trust and SASE. This is the landscape every IT leader must be comfortable navigating. When I teach wireless networking, I emphasize that Wi-Fi is far more than just internet without cables. There are standards, security layers, and network design decisions that directly impact performance and cybersecurity. Let's start with Wi-Fi standards. Over the years, wireless technology has evolved through versions like 802.11n, 802.11 AC, Wi-Fi 5, and the more current 802.11x, Wi-Fi 6, and 6E. Each generation improves speed, range, and efficiency. Wi-Fi 6E even opens up the 6 GHz spectrum, reducing congestion and improving performance dramatically. Understanding these standards helps us design networks that support dense environments, think offices, schools, or manufacturing floors. Next is encryption, which is absolutely critical. Wireless networks are inherently more exposed because signals travel through the air. That means anyone in range could potentially listen if the network isn't secured properly. That's why we use strong encryption standards like WPA2 and now WPA3, which offer much stronger protection. As cybersecurity professionals, we must ensure that wireless networks always use modern encryption and never leave default or outdated security enabled. Finally, we talk about guest versus internal networks. This is a fundamental design principle. Internal networks are for employees, corporate systems, and devices that require access to sensitive resources. Guest networks are isolated spaces for visitors, contractors, or personal devices. The reason for this separation is simple. We want to prevent untrusted devices from touching internal systems. Guest networks should sit on their own VLAN with strict segmentation and access control. This protects sensitive business resources while still providing convenience for visitors and mobile users. So when you look at Wi-Fi standards, encryption, and the separation of internal and guest networks, you're really seeing three pillars of secure wireless design: modern technology, strong protection, and smart segmentation. When I cover modern network security, I like to show students how multiple layers work together to create a defense-in-depth strategy. These 5 components, firewalls, VPNs, IDS, IPS, encryption, and zero trust, are core pillars of any secure network architecture. Let's begin with firewalls. I always describe a firewall as the network security gatekeeper. It decides what traffic is allowed in, what leaves the network, and what gets blocked. Today's firewalls are next generation, meaning they inspect traffic far beyond ports and IPs. They analyze applications, behaviors, and even user identities. A well-configured firewall is one of the strongest security controls an organization can have. Next are VPNs, virtual private networks. VPNs create encrypted tunnels that protect data as it travels over untrusted networks. Whether employees are remote, traveling, or accessing cloud resources, VPNs ensure their traffic can't be intercepted or tampered with. But as remote work has exploded, VPNs have also become high-value targets, meaning configuration, monitoring, and multi-factor authentication are essential. Then we have IDS and IPS, intrusion detection and intrusion prevention systems. An IDS monitors network traffic and alerts when suspicious behavior is detected. An IPS goes a step further by actively blocking or stopping the threat in real time. These systems work like the network's threat radar, identifying anomalies, attacks, and malicious traffic. They're critical for early detection and fast response. Encryption is another cornerstone of cybersecurity. It protects data both at rest and in transit, ensuring that even if someone intercepts or steals the information, they can't read it. Encryption underpins everything from HTTPS to Wi-Fi to secure email to full disk protection. Without encryption, modern cybersecurity simply wouldn't exist. Finally, we have zero trust, the new mindset for modern security. Zero trust assumes no user, device, or network segment is automatically trusted, even if they're inside the organization's perimeter. Every request must be verified, every device must be authenticated, access is limited to exactly what users need and nothing more. Zero trust shifts security from a perimeter-based model to an identity-based strategy. Put together, these 5 controls, firewalls, VPNs, IDS, IPS, encryption, and zero trust, form a layered modern defense strategy. They protect the perimeter, secure remote access, monitor for threats, safeguard data, and ensure that trust is never automatic. This is the blueprint for securing today's distributed cloud-connected environments. In the cloud, instead of plugging cables into switches and routers, we design entire networks in software. Whether you're in AWS, Azure, or Google Cloud, you create VPCs or VNets that behave like data center networks. You control IP ranges, subnets, routing tables, gateways, the whole structure. Virtual networks let us isolate workloads, segment environments, and manage traffic flow exactly the way we would on-prem, but with the flexibility and speed of the cloud. Next are security groups. These function like lightweight, instance-level firewalls. Security groups define which traffic is allowed in and out of a specific server, container, or service. They're stateful, easy to manage, and a core part of cloud security architecture. I remind students that security groups enforce least privilege at the network layer. Only the right ports, only the right protocols, only from the right sources. Then we have load balancers, which distribute traffic across multiple servers or services to ensure reliability, performance, and high availability. Load balancers prevent any single system from being overwhelmed. Cloud platforms make this incredibly efficient by auto-scaling to match demand, something that used to require a lot of hardware and planning in traditional environments. Finally, cloud firewalls. These are the cloud-native equivalent of perimeter firewalls in a physical data center, but with far more flexibility. Cloud firewalls can sit at the edge of a VPC, between subnets, or even at the application layer. They can enforce policies across an entire environment. Modern cloud firewalls integrate with identity, threat intelligence, and automation. They're a critical piece of zero trust in the cloud. So when we bring these together, virtual networks, security groups, load balancers, and cloud firewalls, we're really mapping out the foundation of cloud architecture. These tools allow us to build secure, scalable, resilient systems that can handle modern workloads and adapt instantly to business needs. Traditionally, security teams relied on signatures or known attack patterns, but threats evolved too quickly for that alone. AI takes a behavioral approach. It learns what normal looks like inside a network, a system, or a user's activity. Then, when something deviates from that baseline, the system flags it. Whether it's unusual login locations, sudden spikes in traffic, strange process behavior, or data exfiltration patterns, AI catches things humans would never spot manually. Next is automated response. Once we detect an anomaly, speed matters. In many attacks, the difference between a minor incident and a catastrophic breach is measured in minutes. AI-driven systems can isolate endpoints, disable accounts, block network connections, or roll back malicious changes instantly. This doesn't replace human analysts, it empowers them. Instead of spending hours triaging noise, analysts can focus on strategic investigation while automation handles the time-critical work. Finally, there's optimization. AI helps organizations run smarter, not just safer. It automatically tunes network performance, assigns resources more efficiently, predicts failures before they occur, and even recommends configuration improvements. In cybersecurity, optimization means reducing false positives, prioritizing alerts more accurately, and improving overall system resilience. So when you bring these together, anomaly detection, automated response, and optimization, you get a network and security ecosystem that is intelligent, proactive, and adaptive. This is where IT is headed, and as leaders in this space, it's critical we understand how to leverage these capabilities in our environments. That's all the time we have for this episode of Technology and Cybersecurity Explained. I had a great time, and I'll see you next time for even more insights.